This video is on section 11.5, the binomial theorem. Here are the objectives. We will determine binomial coefficients, apply the binomial theorem, and then identify specific terms once we have expanded the binomial. A few things I want to remind you of is that a binomial is something with two terms, for example, a plus b. If we square this binomial, we know that we can write this as a plus b times itself, and then we would FOIL it out to get this. Well, this is known as a binomial expansion, and what we've done is we've taken this and expanded it. And sometimes we will have powers bigger than 2. Maybe this is a plus b to the 7th power. And if that's the case, it will take a long time to do this, as illustrated on the next page. So here, I have expanded everything up to the 5th power for you. Okay, and I want you to notice some patterns here. So go ahead and pause this and see if you can identify some different patterns. Look at the coefficients. The coefficients are the numbers in blue. Look at the exponents and see what types of things you notice. You may notice that from an expansion, just a general expansion, the exponent on the first term decreases from n to 0 from left to right, whereas the exponent on b increases from 0 to n from left to right. You may have also noticed that the sum on each term is the degree. And finally, the number of terms is important to notice. The number of terms is n plus 1. So if I have an exponent of 4, when I expand this, I will have 5 terms. Now, the coefficients, or the numbers that are in front, can be found by utilizing something called Pascal's triangle. And basically, Pascal's triangle begins with a 1, and then in the next row, it also has 1s. But then what we do is down each side, we always have 1s. But to get the numbers in the middle, we simply add. So we'll add these to get 3, add these to get 3. So 1, add these to get 4, add these to get 6, add these to get 4, and 1, so on and so forth. This is a degree of 0, degree 1, 2, 3, 4, 5. Now, this is helpful in order to find the coefficients. So this is what I illustrated to you on a previous slide, and I want you to notice what's written in blue is the same thing we have here in Pascal's triangle. So the first row of the triangle is degree 0, degree 1, degree 2, degree 3, degree 4, degree 5. And these are the numbers that will be found as the coefficients. Let's see if we can use Pascal's triangle and expand the following binomial. Okay, so we want to expand the binomial a plus b to the 7th power. Now, on the previous slide, we had Pascal's triangle, and I'm just going to write that last row. It was 1, 5, 10, 10, 5, 1. And this represents degree 5. So what I can do is I can add 2 more rows to get degree 7, and then I will know the coefficients. So remember, we start with 1, we multiply these, we add. Add to get 6, add to get 15, 20, 15, 6, and 1. If we do this one more time, we will have degree 7. And you should notice the pattern when looking at Pascal's triangle. Okay, so here are the coefficients of degree 7. So now that we know the coefficients, we need to analyze the variables and the exponents. So when I write my first term, I have a coefficient of 1, a, and remember a is to the power of 7. Then I keep moving along, so my coefficient is 7. Now I'm going to have an a, but I'm going to subtract 1 from the previous exponent to get 6, and then I'm going to add the b. And as I proceed to the right, I will subtract 1 from a, add 1 to b. So my next term is 21a to the 5th b squared plus 35a to the 4th b cubed plus 35a cubed b to the 4th plus 21a squared b to the 5th plus 7a to the 1st b to the 6th plus b. Or, b to the 7th. You can put a 1 there if you want. And this, all of this is the binomial expansion of this. So these two things are equivalent to one another. Let's try another example. Expand the quantity a plus b to the 8th power. Now, in the previous example, we had the final row of Pascal's triangle was to the 7th power, and it was the following. So if I want to expand this to the 8th power, then I need one more row here, and I will find that now. So these are the coefficients of the binomial expansion. We will start with 1a to the power of 8 plus 8 times a to the power of 7, because I take 1 away from the first, times b to the power of 1. And remember, for my exponents, as I move to the right, I will take 1 away from a and add 1 to b. So my next term becomes 28a to the 6th b squared plus 56a to the 5th b cubed plus 70a to the 4th b to the 4th plus 56a cubed b to the 5th plus 28a squared b to the 6th plus 8a b to the 7th plus 1b to the 8th power. And that is the answer. Now, Pascal's triangle is nice, But if we want to expand a binomial to a power that's relatively large, writing all the rows of Pascal's triangle could be cumbersome. So here is an alternative to Pascal's triangle. And this alternative is found by using combinations, or this n choose r. Now this n choose r with this notation represents the binomial coefficients, and it is found by this formula here. So we've already talked about factorial, so we'll take n factorial divided by r factorial times the difference of the two factorial. In your readings, you will often see this notation, and this just means n choose r. So there is this notation as well as this notation, and they mean the same thing. Let's practice. Okay, so we want to evaluate each of these. And I just want to remind you of the formula. N choose r is found by taking n factorial divided by r factorial times the quantity n minus r factorial. So in our first example, we will have 4 factorial divided by 2 factorial times the quantity 4 minus 2 factorial. This will be equal to 4 factorial over 2 factorial times 2 factorial. Well, hopefully you remember some of the rules. So remember, I can rewrite 4 factorial as 4 times 3 times 2 factorial. And then one of these will cancel out on the bottom. This becomes 12 divided by 2, which is 6. Let's try number 3 here. 10 choose 7 would be represented as 10 factorial over 7 factorial times the quantity 10 minus 7 factorial. When I rewrite this, I have 10 factorial over 7 factorial times 3 factorial. And we may want to simplify this a bit. So 10 times 9 times 8 times 7 factorial. We'll cancel these out. And this will end up being 120. And the last one, 10 choose 3. 10 factorial over 3 factorial times the quantity 10 minus 3 factorial becomes 10 factorial over 3 factorial times 7 factorial. Well, these are the same exact thing, so we know that this answer is 120. There are some special cases, and that is when you choose 0 or when you choose 5, given 5. So if these are the same number, the outcome will be the same. And here's what happens. Let's just see what happens when we plug this into our formula. This would be equal to 5 factorial over 0 factorial times 5 minus 0 factorial. Well, hopefully you remember from our earlier studies that this is just equal to 1. So we end up with 5 factorial over 5 factorial, which is equal to 1. So anytime this is a 0, you will end up with 1. Similarly, over here, if I plug this into my formula, I'll have 5 factorial over 5 factorial times 5 minus 5 factorial. Well, a couple things can happen here, but this results in 0. So 5 factorial over 5 factorial times 0 factorial. This is 1. This cancels, leaving us with 1 once again. So anytime these are the same, the result will be 1. Now, there is a button on your calculator to help you find these factorial, or to help you find these values without using the formula. And if you go, and this is for a TI, if you go to math and then arrow to probability, and then NCR will give you this result. Okay, so again, this helps us identify the coefficients. So there is something called the binomial theorem. And the binomial theorem says that the expansion is given by all of this. And we've already done this. So all of these variables and exponents, we've already done that. It's all the same. But the new part are the coefficients. And the coefficients are now found by these combinations, these n choose r's. So basically, this here is the formula. It is the summation of all of this. So if n is 8, for example, we would have 8 choose 0, 8 choose 1, 8 choose 2, so on and so forth. So this is just another way of finding the coefficients of the expansion rather than using Pascal's triangle. So let's go ahead and do some examples. Okay. So the first thing I want to do is expand this. Now, one thing I want you to notice is this is a little bit different than our previous problems because now I don't have a binomial with just variables. Now I have numbers attached to these variables. So we need to be very, very careful. I'm just going to write down this binomial theorem real quick. Just so you can kind of see. Okay, so let's begin. This will be equal to, the coefficient will be found by taking this n choose r. In our case, n is 5, and we're going to choose 0. Then we start with the first term, and we raise that to a power of 5. Then, to get the second term, we have 5 choose 1. We take 3y to the power of 4, and we multiply that by 2z to the power of 1. And we just move along. 5 choose 2. 3y is now raised to a power of 3, while 2z is raised to a power of 2. 5 choose 3. 3y to the power of 4, 2z to the power of 3. Oops, I'm sorry, this should be 2 and 3. Plus 5 choose 4, 3y to the power of 1 times 2z to the power of 4. And our last term is 5 choose 5. We don't have any more 3y's, but we have 2z to the power of 5. Okay, so now we need to evaluate each of these terms. So let's start with the first one. 5 choose 0 we found was to be 1. Now what I need to do is I need to raise 3 to the power of 5 and y to the power of 5. This will become 243y to the 5th. Then our next term, 5 choose 1 is 5. 3 to the 4th is 81 y to the 4th. and then 2z. So I need to multiply all of this. And when I do, I should have 810 y to the 4th z. Same thing in the next one. 5 choose 2 is 10. 3 cubed is 27 y cubed. And 4z squared. We'll need to multiply each of those. And when we do, we have 1080 y cubed z squared. Onward, 5 choose 3 is 10. 3 squared is 9 y squared. And 8z cubed. Multiplying those, we get 720 y squared z cubed. Then 5 choose 4 is 5. 3y, and this is 16z to the 4th. We need to multiply those. And when we do, we get 240 y z to the 4th. Our last term, 5 choose 5 is 1. 2 to the 5th power is 32, and then we have z to the 5th power. So we have plus 32z to the 5th. And this is the final answer. I want to do another example, and you are certainly welcome to try this one on your own, but before you do, I want to point out one major difference. The major difference is this minus sign here. So as you are expanding this, be very cautious of this minus sign. Okay, so as we expand this, remember 4 is n. So I'm going to have 4 choose 0 times my first term to the power of 4 plus 4 choose 1, my first term to the power of 3, and then my second term. And when I write my second term, I'm going to include that minus sign there. Plus 4 choose 2. Y squared to the power of 2 times negative 5z squared plus 4 choose 3 y squared to the first negative 5z cubed plus 4 choose 4 y, oh, this one goes away. So negative 5z to the power of 4. All right, so notice these are negative. Now, the power that these values are raised to is very important. Remember, if it is odd, the outcome will be negative. If this number is even, the outcome will be positive. So what's going to happen here is we are going to end up with alternating signs. So when we expand this, 4 choose 0 is 1. Remember, a power to a power you multiply, so our first term is y to the 8th. Now all of this over here, 4 choose 1 is 4. This is y to the power of 6. This is going to be a negative 5z. So when I multiply all of this, I get a negative 20 y to the 6th z. Moving on to the next term, 4 choose 2 is 6. Power to a power you multiply. Now this is negative 5 squared. So this will have a positive outcome of 25. So I'm going to have to multiply all of those, and I get 150 y to the 4th z squared. This term results in a negative 500 y squared z cubed. This one is going to be positive because we have an even exponent, and it will be 625z to the power of 4. And this here is the final answer. Go ahead and give this one a try. Okay, when you expand this, n is 3, and be cautious of this negative sign. So we will have 3 choose 0 times t to the 4th cubed plus 3 choose 1 times t to the 4th squared times a negative 3v to the 1st plus 3 choose 2 t to the power of 4 to the 1st power times negative 3v squared. And then the last term, I know this is the last term because I have 3 choose 3. I can't take 3 choose 4, that's just not possible. And this will be negative 3v cubed. When you expand this, the final answer should be 8 t to the 12th, sorry that's sloppy, minus 36 t to the 8th v plus 54 t to the 4th v squared minus 27v cubed. Notice the alternating signs. There will be occasions in which we will want to find a specific term of a binomial expansion. Maybe I want to find the third term of some binomial raised to the 11th power. Well, what I can do is remember that the whole exponent pattern, right? And I want you to remember that these values, or I want you to notice rather, these values match. Okay, so that's something that's kind of helpful. But the reason this is helpful is because there's a formula for this. So if I want to find the kth term, maybe it's the 7th term, for example, of this, I can apply this formula here. And I know that this looks pretty complicated, but really here's what's happening. So n is the exponent, so anywhere you see n, that's the exponent. Now this k minus 1, if I want to find the 7th term, for example, well then this is just 6. 6, 6. Okay, so it's nothing crazy, but you'll want to make sure that you remember this formula. Let's see how it works. Oh, what do you know? Let's find the 7th term of this. Now, yeah, you could take the time and expand this and write out all the 10 terms and then count to the 7th one and find it that way. But we don't have all that time, and instead we can use the following formula. N choose k minus 1 times a to the power of n minus k minus 1 times b to the k minus 1. Okay, well, n is 9. K is 7. So let's plug in what we know. This is n choose k minus 1. Well, if k is 7, 7 minus 1 is 6. This is a, this is b. So we will have x to the power of 9 minus, again, this is 7 minus 1, which is 6. And then b is negative 3y to the k minus 1. Well, that's 7 minus 1 again, which is 6. Okay, well, we can plug this into our calculator. 9 choose 6 is 84. This simplifies to x to the power of 3. Remember, if we have a negative to an even power, this is going to come out positive. So this will be 729 y to the power of 6. Multiplying this all out, I get 61,236 x cubed y to the 6th. And that's the final answer. Go ahead and try this one on your own. Unfortunately, I'm sorry, this is also the 7th term of something raised to the power of 9, so that is kind of similar. So again, our formula is n choose k minus 1 times a to the n minus k minus 1 times b to the power of k minus 1. K is 7, n is 9, so this becomes 9 choose 6 again. A is 3c, and we will have that to 9 minus 7 minus 1, which is 6. B is d to the 5th power to the power of k minus 1, or 7 minus 1, which is 6. This is 84. This is just 3, so 3c cubed. 3 cubed is 27 times c cubed. Power to a power, you multiply, this is d to the power of 30. When you multiply this all out, the final answer is 22,000, or I'm sorry, it is 2,268 c cubed d to the power of 30. And that concludes this video.